Okay, welcome everybody. Thank you very much for coming. I'm Paul Manuel, by the way, so I'm the Director of Digital at Multiplay. I'm not going to bang on about what we do, but hopefully that'll become clear from the talks that you listen to today. So the talks today is all going to be about Titanfall. It's an end-to-end story, so you're going to hear from the studio. So Jon Shiring from Respawn will be kicking things off, talking about the online tech of Titanfall. Thank you, Jon. The next part of the chain is Multiplay. So we're game hosting specialists, and if you don't know what one of those is, you will do by the end of this talk. And you're going to hear from our CTO, Steve Hartland, who's going to talk about the platform that we've built that actually hosts Titanfall. And then at the end, there's a whole bunch of infrastructure and cloud that sits on the back of that. And Google Cloud are here to talk. So that's Miles. And the title of your talk is? Reducing the PETA per DAO. Which stands for?
Reducing the pain in the ass per daily active user.
So, which we can all relate to. So that's what Miles is going to be talking about. So thanks again for coming out. I think I'll hand over to Jon.
All right. So you will be hearing from 3 different speakers, as he said. We'll do a little short Q&A after each one, but try to keep it moving. Speaking of which, so my talk is going to be very dense. I'm going to try to move quickly. Hopefully you can follow along or ask me lots of questions in the Q&A. So just to start off, Titanfall 2 came out in fall of last year. It's on PS4, Xbox One, PC. And as we go through this, I want to make one thing really clear, and that is please don't assume that I'm the person who wrote all the code that we're going to be talking about. In particular, I would really like to call out Mike Kalis, who did a lot of the matchmaking and server allocation and deallocation work. And he was just incredibly tireless and careful about doing all this stuff so that it works so well. So I want to point out that Mike is awesome. All right. So for people who are really interested in Titanfall, I did an earlier tech talk about Titanfall 1. You can find that one on YouTube if you're curious. It's a much deeper dive into all the online stuff for Titanfall 1. So you don't have to have watched it, though. But just to kind of do a quick review here. So Titanfall uses a client-server architecture. What that means is it's kind of the dumb client model. The clients are untrusted. They do all the work on the servers, and the servers are running kind of a very expensive simulation, so we end up using a lot of compute power. We're 100% on dedicated servers, no player hosting, and our servers automatically scale up and down, which we're going to be spending a bunch of time today talking about. Our dedicated servers are Windows binaries. They're just Win32xes. We're not doing anything particularly Windowsy with them. We're just reading and writing packets. And we have a backend that we call Strider. And Strider is sort of the, it's web tech, and it sort of like runs the whole simulation. So it spins up game servers, you play a match on it, it's handling all the kind of interesting bits there. So Titanfall 1 was, we hosted the game servers 100% on Microsoft's Azure. You probably saw some ads at the time for that. And one of the big changes on Titanfall 2 is we're now a mixture. So we're using what's called bare metal, and we're on multiple clouds. So let's talk about why. So first of all, bare metal is kind of a phrase that's not obvious to everybody. Bare metal and cloud is still the same tech. There's really not a huge tech difference there. It's not that one gives you access to anything the other doesn't. So they're both just servers and racks. So the main difference is actually on the business model. So on bare metal, you're mostly renting servers by the month is kind of the way it normally works out. So what we found is just after a few days, you can rent it for shorter, but after a few days of renting it by the day, it's the same price as by the month. So you might as well assume that you're going to be paying a month at a time for these servers. Cloud, as some people will know, you can spin it up whenever you want. You can spin it down when you're done. And that business model ends up having a lot of ramifications for how you use them. Generally speaking, if you're going to be buying servers by the minute, it's cheaper to buy in bulk. And so when you see the actual cost difference between cloud and bare metal, it's really stark. We're paying more for bandwidth on cloud than we are for the entire server on bare metal. So it really needs to work out so that you're using it when you need it and you shut it down when you don't, so that the per hour cost comes out so that both are competitive with each other. Because as we'll talk about with games, you don't always need the servers running. It's very regional, and you get a peak and a drop every day. So it's like a sine curve. So we don't actually need those servers running for most of the day. But with the economics the way they are, it ends up being cheaper to run them most of the day anyway for a good chunk of your servers, but not all. So on top of this stark cost difference, we also lose about 20% of the CPU to the VM overhead. Bare metal, kind of by the name, you generally, if you're getting some places, will give you bare metal with no VM. So you'll get the bare metal. There's other ones that do run VMs, so you might have an equivalent loss there. but cloud is always on a VM. And so for the same price we're paying, we're actually getting a little bit less compute on the cloud than we do in bare metal. So what we found on Titanfall 2 is if we actually need a server instance to run for more than 4 hours a day, it's cheaper to run it in bare metal. So this is 1 week of one data center. This is US East, which tends to be our biggest. So you can see kind of the weekends in the middle here. You can see every day we have, goes up in a peak, comes back down. So what we end up doing is running a really good chunk of that in bare metal, and then we burst into the cloud every day. So that's why we use bare metal, and that is a big change on Titanfall 2. But why would we be on multiple clouds? We've been accused of being insane for being on multiple clouds, but I think we have a pretty good reason for it. So first is the cloud is not infinite. You can still run out of servers in the cloud. So we are 2 for 2 on running out of servers in a cloud in at least one data center during a significant launch. Also, you'll find that clouds are not equivalent. So we really care about latency. We're trying to put players on servers that are near them so we can have a good ping. And for instance, AWS has no Midwest data centers. So if you're looking to start a match in the Midwest, I would advise you not to use AWS. And so other ones, we'll talk. Google in 2016, they did not have a South America or an Australia data center. So what you'll find is that for different regions of the world, one cloud will have an obvious advantage over the other for the geography, cost aside. So one thing you're going to have to get used to is external launch planning. Because you can run out of servers, even if you're doing something like this, you need to give estimates weeks or months ahead of time. Bare metal especially, they are not sitting there with a bunch of servers waiting for you to come use them like cloud is, because that's not their business model. So you need to give them lead time to go buy and rack these machines, which can be months. And then obviously even on cloud, you still need to give them estimates, not as far ahead, but since you can run out, you need to warn them if you're going to use them. So what I've talked about in the past is that estimates on how many players are going to show up on any launch is wildly wrong, either direction, all the time. And the farther away from launch you do it, the more wildly off it'll be. So this ends up being a risk for everyone. If we tell them we're going to need a lot more servers than we end up using, they are obviously not happy about that. If we get it wrong the other way, we'll run out sooner. So this is kind of the curve that we're looking at for the costing on Titanfall 2. So if we were 100% cloud, we would be paying quite a bit of money. If we are 100% bare metal, it's a lot cheaper, but you're never going to get your estimate right. So if you're going to be paranoid and go 200% bare metal, you're almost back up to the cost of 100% cloud. So we're doing a mix of the two, where we try to estimate the best we can. We figure out, it's all a spreadsheet on how many servers you're going to need for more than 4 hours a day, how many you're going to need for less. And we try to get it right. If we're wrong, we're just going to kind of, be back and forth on that curve, and we're not really going to get killed either way. Obviously, the better our estimate is, the cheaper it'll be. But it's, we're already down in a region where if we get it right, it's 75% less than the 100% cloud cost. So being wrong is still a huge cost savings over the let's just go all cloud all the time. So just to cover it, we're running mostly in bare metal most of the day, burst into cloud on the top of the peak, we come back down out of the cloud. And we really care about the global coverage of all these data centers all over the world. And what we found is this is actually really resilient. So during we had a tech test, you can call it a beta if you want. We actually had a hacker group DDoS one of our data centers in the Midwest. It was one of our bare metal. And so we saw the data centers, the traffic was just overwhelming them. It was one of these new insanely huge ones. And so what we actually did is Multiplay just stopped allocating servers in the bare metal. We moved all the matches into the cloud. So we kind of just exited that data center completely, still in the Midwest. And so within about 15 minutes, we had completely exited that data center and everyone was back to playing again with no impact. So it actually gave us the ability to kind of, I wouldn't say outmaneuver the hackers, but it gave us a possible solution so that we weren't completely destroyed by them. So that's kind of the economics of how we're running our servers, but let's talk about how to actually do it in a way that works well for players and makes sense. So Titanfall 1, we learned a lot of lessons on it. And we had a really, really simple matchmaking system, and that was kind of by design. It was our first game launch. So the way it worked was when you searched for a playlist, we would look for an existing game to throw you in. If we couldn't find an existing game that was good enough and we waited long enough, we would just spin up a brand new server, put you on it, and wait for other people to find you. It's very simple. It worked pretty well, but had a lot of issues, which we're going to talk about. So one of the things is because we would plop you on that server and then ignore you, basically, that server was now trying to figure out what to do with all these players. So it would shuffle teams between rounds. It would try to figure out what to do with filling up the server and that kind of thing. So the servers themselves were kind of acting with agency. And the servers were saying, you know, this match isn't full. We're this far in. Let's try to find a player to fill it. You're trying to balance disparate skill levels. And it doesn't work that great, and we'll talk about why. But also, the server will set a timer when it becomes empty. When that timer hits a certain amount, it'll shut itself down. So you can kind of think of it as we're spinning up all these independent agents that are all trying to figure out what's best for them and shut themselves down when they don't think they're needed anymore. So first thing is our player base was fragmented across all our servers. So here's an example. You're playing a match on Angel City. An hour ago, it was 12 out of 12 players. It was really fun. But over that hour, people have dropped. So now it's 7 out of 12. It feels like a different game. There's a lot less things happening. There's less players to shoot at. And so it doesn't quite feel, it's not even the same experience. Two people playing, depending on time of day, are going to feel that Titanfall has a very different experience within the game. So what we found is the problem with this, sorry, let me back up. If between matches, when you're in that lobby countdown, the servers will be trying to merge with another server. And so that's our chance to, when people are quitting, to try to find servers that aren't quite full, merge them together, make a full match, so you don't feel the exit of players past peak every day. What we found is we can only do that if the servers actually fit together. So what we found is we have lots of servers that are not quite full, but they're not below 50%. And so if most of your servers are above 50% full, we can't actually merge them. So we kind of had this pattern where in the back half of every day, you know, you'd have a match that was 12 out of 12, 11 out of 12, 10 out of 12, and it would kind of slowly work its way down. And we didn't really have a lot of servers that were 1 out of 12 or 2 out of 12 to merge them with. And so this nice simple system didn't end up serving us as well as we wanted. We really want nice full matches. So we also had skill fragmentation. So after every match, we kind of figure out the results of it, adjust everyone's skill based on how we expected them to do, and then shuffle the teams around and try to make a new match. But what we found is, like, once you've made a bad decision, it's really hard to fix it. We have the classic case is you'll have one really good player on one team, and to fix it, you start going down this route of, let's find another really good player and put them on the other team. And then the first pro player quits, and you're back to the same exact spot. So you're always, we've made this bad decision in the past. How do we fix it? Let's make a new bad decision. And we didn't really have a way of kind of fixing all this. So it ended up being really hard. We had wild skill ranges, and because of that, the pro players weren't really that challenged. The kind of low to medium skill players were just getting randomly crushed by some players, but not others. Not a great experience from our perspective. So next, let's talk more about other fragmentation here. So we have another one, what I would call VM core fragmentation. So our tech last time would take a giant box, carve it up into little 2-core VMs, and then run one instance of our game server on each VM. And this is a full Windows VM. So we take basically a 32-core machine, run 16 2-core VMs on it. And the reason for that was our game server used 2 threads. We had one that was really doing all the expensive simulation and another thread that would kind of help out on writing updates to clients. But that helper thread it used at best half a core, and often quite a lot less than that. And even our main core wasn't using a full, our main thread wasn't using a full core all the time. So we had pretty poor utilization of that 2-core VM. And so we ended up having kind of worst case. We'd reserved the worst case, but we weren't using the worst case. So when you look at the numbers, about at least 25% of all the compute that we were paying for was actually just sitting idle. And that was kind of unfixable by design at the time. So we also have what I would call VM fragmentation. So let's go back to the Angel City match. You're in this cool 12 out of 12. The player base is growing. All our servers are full. Then an hour later, we're now down to 1 VM still in this giant box. All the others are shutting themselves down because they're not needed anymore. And so what we really had figured out was a way to run a single 7-player game on a 32-core machine. Not an awesome experience, and not something I'm super excited about. And because of the VM isolation, all each instance knew is it was a VM running on something. It had no idea what all the neighbors were, And so we couldn't detect it. But even if we could detect it, I couldn't actually fix it because we had no way of kicking players out or fixing these old past bad decisions, as I said. So kind of the back half of every daily curve is a mess. On the way up, we're doing lots of allocations, and that lets us be really efficient. On the way down, we're only doing deallocations. There's not enough new people joining the game. There's more people leaving than joining. And so we had this really messy situation kind of half of every day. And we did what we could to merge servers and handle it. So it wasn't total disaster, but it definitely wasn't great. So for the beginning of Titanfall 2, we looked at all these issues and we said, how do we fix this? We have all this fragmentation. We have lots and lots of problems where we're good on allocations and really bad on deallocations. And so first thing was obviously stop using these small VMs. So with Multiplay's tech, we now take that giant 32-core box and we just run lots of instances next to each other on it. So it's okay if even the main thread isn't using a full core. We can run lots of these helper cores or helper threads, and they'll kind of aggregate themselves out. So we can run a lot more of them. So it's a little unfair because we optimized a lot of the code, but we also doubled our snapshot rate. So it's not really a fair comparison. But even still, with all these things and getting off the small VMs, we can still run about 50% more instances of our game servers on each of these giant boxes than we could in Titanfall 1. So we kind of talked about this of if the right thing to do for these players who are having a bad experience is to back out and search again, why don't we automate it and do it for them? And then why don't we do that for everyone all the time? So in Titanfall 2, between every match, instead of having them sit on the server that's trying to figure out how it can make the best of the situation, we blow up the whole match, send everyone back into matchmaking so we can make all new decisions. So just because we put a really high skill player on one team, it is irrelevant now because he's just back in the matchmaking pool. It doesn't matter that in the past we put him in a bad match, and that goes for the whole skill curve. But it also means that we have defragged everything. We can now, every 15 minutes or so, assuming a match time of 10 to 15 minutes, we can fully reallocate all our servers. We can move them around host to host. We can fix all the fragmentation on VMs and cores and players and skill. And so that one change just made all these problems much better. We can have full matches every time. We can find you an interesting match every time. And so it gives us the ability to do allocations even when the player base is dropping. And that's really critical. So one person, that's me, said, if your matchmaker has to handle high scale, you're doing it wrong. Turns out that dude's an idiot. So in Titanfall 2, our matchmaker is really busy. We end up having about 5% of our entire player base in matchmaking all the time because of this change. So our matchmaker is doing a whole lot of work now. And it has to be really fast because of it. And that was something that took us a little time to get right. So when you go into matchmaking, we kind of bin players into these different things, and it's regional. So it's data center and playlist and kind of to some degree skill. We sort them by skill. We chop them up into little matches. We allocate a server, and that's through the Multiplay APIs that we'll talk about. And then we post that server info back to those players and say, here's your match, go play. And then 15 minutes later, they're going to come back and we're going to repeat it. So let's talk a little bit more about the division of labor on allocating a server. So what we end up doing is we go to Multiplay's API and say, we want a server in the East US. And we pass in a build name so they know which one, so we can have multiple builds running at the same time. Multiplay will figure out, do we have bare metal that's sitting idle? Can I put it there? Or if not, which cloud are we in? And they handle that entire decision for us. So all we say is East Coast US, and they go off and figure out where to run that server. Then they're also watching the curve of allocations from us and predicting ahead. So if it takes 7 or 20 minutes to spin up a server on the cloud, they'll have figured that out 7 minutes before so that our allocations aren't actually being slowed down by this. And so what we're doing is these fast allocations, they're coming back very quickly, but behind the scenes, they're doing this very expensive curve prediction and doing all this thing ahead of time. And so once they do the allocation, they boot the physical server, they copy all the builds onto it, they apply any patches they need to, and then they run our exe. And that exe will talk to Strider, which is how we know it comes alive. So most of our allocations take milliseconds. Existing servers don't actually need to reboot to get allocated again. So our exe will just keep running. We'll ask for an allocation, they'll just hand it right back to us. So most of the time on our graph, it's really, really fast. But at the same time, there are still really rare times where they couldn't have predicted it. And that mostly happens in development, where we upload a build and our entire QA team starts playing at the same time. So there are times in development where we have to wait for this very long, expensive allocation. But in retail, it doesn't happen that much. And so we end up running a fixed amount of bare metal just for dev to handle this case, because we don't want our QA team sitting around for 10 minutes every day. And because we test enough builds all the time that it's worth it. So there's some pros and cons in the design choices we made on Titanfall 2. There's a lot of pros. We can really quickly defragment our servers. We can move them out of expensive cloud into bare metal. We can also scale up and down very quickly because of this. And we're way more efficient at shutting down unused capacity. Kind of in the Titanfall 1 model where the server sits idle long enough and it shuts itself down. If you have a whole bunch of servers that are not quite idle, but they're getting used often enough in a random distribution that they're going to stick around, we kind of chase the curve down in a not really cost-effective way. And it works, but it could be a lot better at figuring out when we no longer need a server anymore. And in Titanfall 2, we're doing these deallocations now really quickly because Strider is handling all of the matchmaking. And so we know exactly how many servers we need with every matchmaking frame, and spinning down the ones we don't need anymore. And Multiplay is able to handle these allocations quickly, so we could be really nimble with that. And obviously, because of the defragmentation, we have much better skill. We have full matches. The player experience is just way better. But the con is that we're doing many more times allocations than in Titanfall 1. In Titanfall 1, the server would get allocated and it would just run for potentially hours and then shut itself down. So our dependency on these allocations is a lot higher. And that means if those allocations failed, we would have an outage really quickly, as opposed to Titanfall 1, where new allocations could fail, but the old servers would just keep running for a while. But that said, when I made this deck, I was happy to say we've had no outages since launch. And then in the past week, the AWS S3 hit us. So we have actually had a hour and a half outage, I would say. And that one is a lesson for us on ever relying on a single cloud. And so there was a dynamic file, our playlist data, that each server would download on boot. And with S3 down, it wasn't able to download the playlist, so we couldn't spin up new servers. So obviously in the future, we're going to be looking at having multiple different URLs at multiple different hosting places so that we can always get those playlists and we're not reliant on any cloud. So just to kind of look back, I want to talk about some conclusions and trends that we've been watching as we do all this. So we are big enough to run out of servers in a cloud, but we're not big enough to really change the economics of it. Bare metal is much cheaper. I'm not going to fix that. And because of that cost difference, it's obviously really tempting to say, I don't want to have to deal with any bare metal. It's hard to predict that far ahead. You have to do a lot of work. The economics of it make it so that it's really hard to ignore. So given that game launches the estimates are unreliable, you're not going to get it right, but just do the best you can. And the closer you get, the cheaper it'll be. And so like one of my real pieces of advice here is, if you're only on bare metal, you should never sleep again, because I feel players should never run out of servers. They should always be able to play your game. It should just feel like it's a service. And so kind of explaining, hey, we mispredicted how many people would come to the game, sorry, is not an okay answer to me. And so you really want, even if you plan to do 100% bare metal, you want to have cloud there. So if your prediction is wrong, game still keeps working, and it's just a little more expensive that way. And so kind of recap, the clouds aren't interchangeable in every region. So even if you really like one, you still want to be on multiple so that you can serve all your players everywhere. That said, Google is opening a lot of data centers in some regions that we cared about this year. So some of this might be a problem in 2016 that won't be a problem in 2017. And my advice to you is be on every cloud. But kind of looking at the code side, not just the economics. So in Titanfall 1, we had all these independent agents. We'd spin up a server and it would figure out what to do. It would talk to other servers. They would merge with each other. We'd do all this work. And in the end, the servers didn't really have a global view. And so the servers couldn't make as good of a decision as we could on Strider. It had less data to work with, and it had kind of much smaller view of the universe. And so for Titanfall 2, we definitely reduced a lot of the decisions that the game servers make and moved them into Strider. And so we're kind of on the steady path of not just kind of the dumb client-server model, but we're kind of been on this trend, this kind of naturally forming trend of kind of dumb servers, where we're going to spin up a server to run a game simulation, run a match, but all the really interesting decision making keeps moving itself out of the servers and into Strider. And so Strider has kind of grown very quickly since we created it in Titanfall 1. And so Strider, one of the reasons for Strider being kind of taking on all this new work is that it's a lot easier to debug. When you have, a few web servers and a few databases talking to each other, it's really easy to figure out what's going on. You can do a lot more monitoring, and we can push changes really trivially, as anyone who's done web stuff knows. So it allows us to do things with less fear, that I'm not spinning up, 10,000 servers with this new code and hoping it goes well. I'm, copying in some new scripts, running them, and adding some debug info so I can see what's happening. And that lack of fear allows us to be a lot more creative and nimble in our choosing how we want to solve things. So kind of looking at the cost considerations, obviously the cloud and bare metal is really different, but it's really different in some wild ways. So the actual hardware, bare metal is cheaper. We'll see if cloud comes down or not. I don't know. Part of this is that business model, whereas if you're going to use it for a little bit and then shut it down, you're going to pay a little more for that variability. Bandwidth. We could try to reduce the bandwidth in our game. Cloud is kind of inexplicably higher on the cost of bandwidth. That might also change, we'll see, but I'm not going to get, 50% reduction in bandwidth. I can work at it and get, 10, 15, 20. And so that one is also, it's not going to change a whole lot, or at least I have no control over it changing a whole lot. I'm sure when you were looking at this, you're looking at that Windows one, though. We're paying so much money for our Windows licenses on cloud, and that is not lost on me. So in the future, we will obviously be looking at moving our dedicated servers off of Windows. Microsoft has kind of heavily incentivized me to move our servers off of Windows. And thanks to Windows 10, which has Linux binary compatibility, we can do a Linux binary for our dedicated server that everyone in our dev studio can run on their own desktop. So they're actually enabling me to do this move for our studio, which is going to save us a lot of money. It still won't actually change our hosting mass significantly, though, because the bandwidth and the cost of the actual hardware is so much more expensive in cloud. We're still going to have, it'll be a different formula, but it's still going to be much cheaper to run in bare metal, at least in the foreseeable future. So that's it. So yeah, to cover all that, we're moving things into Strider. Web tech is definitely something that people should be looking at using for a lot of your transactional stuff. And Strider was kind of a thing that we did on a lark, and then it just kind of took over. So it's this thing that we push all of our new work into. I would definitely recommend anyone play around with web tech if you haven't yet. Yes?
Venturing into the cloud, you had problems with variability of latency amongst your instances and how to tackle that.
So I'll repeat that one. The question was, for hosting in the cloud, have we found variability of latency? And you're speaking of the actual running server, not the allocation time?
Yes.
So we actually have had really good luck with that. We were really worried about noisy neighbors on Titanfall 1. That was kind of our first attempt at doing this. And we found we had no problems whatsoever is the real answer. We also try to allocate kind of a box at a time, or at least a good chunk of a box at a time. So it'll eliminate the on the box noisy neighbor problem. And then the truth is on these data centers, they have so much bandwidth that our game bandwidth is kind of insignificant. AWS is hosting Netflix and things like that are just doing much higher bandwidth than we are. So we haven't had any problems on the sort of networking side either.
What languages and databases and tools you use on Strider?
Question was about what languages and databases and tools we use on Strider. So we, Titanfall 1, because I did web tech around 2000 and then went to go join games, was a lot of PHP because that's what I was familiar with. I know that a lot of people hate PHP. So in Titanfall 2, we've moved a bunch of it to Lua. And a lot of the reason for that is because Nginx, which is our web server, has native Lua, so you don't actually have to spin up. It's really cheap is kind of the real answer. And then kind of, for the back-end stuff, like our Matchmaker is whatever it is, because it's not actually running on a web server. It's running in a process that's kind of churning on the box. We love Redis. Redis is the greatest thing in the world. And we actually started to use a little bit of MySQL on this game for the player's inbox in the networks feature, but that's kind of irrelevant to the Matchmaker and all that. We basically always use Redis unless there's a really strong reason not to. But that will change how you architect your stuff, because the details of Redis, which we won't get into here.
John, thank you very much for your presentation. When you say bare metal, what are you talking about? Outsourced bare metal of other providers, or is it your bare metal plus bare metal providers?
Is Steve? Are you going to cover that, Steve? Should we wait for your talk?
Yeah.
Okay.
Yeah.
Steve's going to go next, and he's going to talk all about that.
Yeah, but the short answer is yes, we do handle all of the bare metal coverage internally ourselves. So, but we also have the ability to do bare metal that you host yourselves.
Yes.
What was the most fun aspect of working on the project over the last 3 years?
What was the most fun? Wow.
You didn't say tough questions.
Honestly, the multiplayer guys, we talk to them all the time. They're basically our friends now. That was a lot of fun. There's some cool features we got to do in the game, and I always enjoy that. It was a fun project. Yes, back there. No, you. Yes, you.
Have you found that there's any regions of the world that even with multiple clouds, you still don't have acceptable latency to?
For sure. Yeah, there's definitely regions, I would say, Middle East, maybe Eastern Russia, South Africa, that we don't have any good coverage right now. That's something we could fix, but honestly, the bigger problem for us is even if we fixed it, we wouldn't have enough players there to support a really healthy ecosystem of matchmaking. So with the options we have for different playlists and all these things happening, there's kind of a minimum population that we would need all the time. And even Australia has a lot of struggles with this, where it's just a very big place that's not very densely populated. So it's really hard to always find someone to match when they want one. So I would say we kind of would have to solve the business side of getting people there to play our game before it becomes more significant to put data centers there. Yes.
Is there a default lobby hold period if your density is lower, off-peak number of players are lesser?
So yeah, we kind of have that thing. If 5% of your players in matchmaking, it means you need a big player base. So the way it ends up working is you'll matchmake until we can find a match. So for the modes that have lower population or the playlists that have lower population, you'll just wait longer before we can get enough to go launch that server.
Do you also vary some of the parameters? Do you vary some of the parameters with, let's say, delta epsilon values to do more iterations?
So we definitely will try to expand the acceptability of what we're looking for to try to fix it, because we don't want to tell people that, sorry, this match is just not possible because we refuse to put you on a server. Where we see that the most is in the US, that basically East and West Coast will expand into Central so that we can put a match there that's decent ping to everybody. Obviously, it's not ideal, but we don't want to just do that right off the bat because we really want to help people play in a region that's close to them. Yeah.
You talked a lot about the dedicated servers being multi-cloud. How about Strider?
Strider right now is just on AWS, Strider actually survived the Amazon outage just fine. It's definitely something that we've talked about, how it'd be nice to have Strider be in more places. It's hard to figure out how to do that with our databases so that it's actually going to work just as well. So for now, we've punted on it, but it's definitely something that I would love to be kind of no fatal dependency on anybody. I shouldn't say no dependency, but yeah, sort of the over reliance on any particular thing it's dangerous. It kind of depends on your tolerance for an outage. There's obviously cost and risk there. So my tolerance is very low for outages. And so we might look at that anyway, but there's no plans in the immediate future.
With the multiple data centers or hosts, I suppose, do you guys have any problems with different performance guarantees and different server types? How did you work around that?
Yes. So we do have real requirements of we need our servers to run well. It's basically highest order for me of when you play our game, it should just feel right and you don't have to worry about any of this stuff. So that is one of the things that I'm hoping Steve will cover in his. We talked to them and said, here's what we require. You should figure out how many of our servers you can run on each type of cloud and bare metal and wherever. And so they kind of handle that for us. So when we do the allocate, they figure out whether there's room for it on a particular server that's already running, or if they need to spin up new physical servers for it. So it is different on different providers, and timings are different on different providers, and there's a lot of complexity there that Multiplay handled for us, so that we could sit back and do this very kind of high level. I want a server on the East Coast, and they do it for us.
One more question.
Yep.
This might be a bit of a mean one. I'm sorry if it is. So the graphs you had in the presentation on the cost saving for hybrid versus cloud only, is that before or after Multiplay?
That is with Multiplay.
Oh,
so
okay.
On Titanfall 1, we were 100% cloud. So we were on the high left of that curve, which gave us a lot of flexibility, but we paid for it, and we didn't necessarily need all that flexibility all the time.
Cool. Cool. Well, thank you very much, John. Hope everybody. So, I hope everybody enjoyed that intro from John there. It's a great insight into what they've been doing on their side of things. So I'm going to be covering and giving you guys an insight today on our technology stack that facilitated all of that multi-cloud and hybrid cloud technology. So first off, I'm sure everybody's aware of the various options. You've got co-location, you've got rented, and you've got cloud capacity, and where each of those strengths and weaknesses are. Obviously, with rented, as John's already covered, you've got essentially a month-by-month contract. It's significantly cheaper. You've got no capex that you would do if you had co-location. I know some of the bigger providers do have their own hardware that they can make use of, and that's a great way of cutting down costs. But if you had all of your capacity in co-location, then it would be significantly cheaper. But on cloud, it gains you significant flexibility, and also a lot of management comes into play. But as we've already covered, we've got limited locations. I know Google is opening, I think, another 8 data centers in the next 12 months. So 10? Oh, he's upgraded. Excellent. So no, there's some significant benefits to be had from cloud capacity. But all of these have the same challenges underneath. So you've still got to be matching that capacity to your player curve. And if you don't get that right, as John said, there's a massive expense that can be had. And not only of that, you've got to actually still get your game deployed to the cloud. So yeah, you've got all of this cloud capacity out there, you've got all the bare metal capacity, but you've still got to distribute your build out to the machines and get them up and running. And then you've got the fact that you've got to monitor this 24/7. All of the game servers, it's a 24/7 business. You've got people playing on Australia at different times as the people playing in the US. And if you don't have the people to support your platform on that 24/7 basis, and there is an issue, you're going to get some angry customers. And one final point is there's a lot of gotchas in this game, especially with game servers. And so experience really does count. And I think we've got quite a bit of it as we've been in the industry for nearly 17 years now. So what are the challenges with game image deployment? I've mentioned global deployment before, but I'm not sure everybody will be aware that when you're transferring images from one location to another location, and those locations are actually a large distance apart, you end up playing with BDP and latency issues, and that it makes it really, really problematic to deploy your game quickly to those remote locations. And while you're trying to deploy it to those locations, if you're deploying to the same physical hardware that's currently running your player base, you also need to make sure that you're keeping the gameplay smooth. There's no point in deploying your new image to your existing infrastructure and having it destroy the gameplay of the game sessions that's going on at the current period of time. That's just not going to wash. So you need to bear all of these facts into account as you're doing the deployment. And zero downtime. You've got games going on 24/7, and you've got gamers that want to play when they want to play. So if you're doing your new DLC patch, or you're doing an emergency patch to fix a nasty exploit bug, you want to be able to roll that patch out and effectively for it to be totally seamless to your end users. And that's what we call zero downtime. And obviously, with all of this, you still want to maintain your cost control. You don't want to have to spend a huge amount of bandwidth costs deploying your build to your infrastructure. And the complexity factors that come into play, obviously, if you've got a multi-platform game, you've got PC, you've got Xbox, and you've got PS4, as well as you're doing multiple providers, Metal, GCE, and AWS, that all adds it up in terms of complexity. And if you're got a stack that can deploy to AWS, it's not necessarily the same stack that can deploy to GCP or Metal, for example. And then on the final thing, you've got multiple builds that are all coming into play. So retail, development, and certification builds all playing at the same time and all vying for resources. And you want to make sure that all of those are given equal opportunity. So what is our process and how do we go about it? First off, it's worth mentioning that the entire stack is built on Golang, Google's language. Here's some yeahs in the crowd there. Yeah, it's not PHP, John. So, yeah, we needed something that was going to be really performant, and we've already expended a significant effort converting some of our existing stack to use Golang. And if you haven't tried it, I can significantly really advise people to go play with it. It gave us the instant benefit that it's multi-platform across the OSs, so we can build the same executable on Linux as we can on Windows and on FreeBSD that we use in some of our core architecture as well. And it's provider agnostic, so we don't have this problem whereby we've got a separate stack that is deploying to AWS, GCP, and Metal. It is a single architecture that deploys to all of them. And we've spent a significant amount of time optimizing it for performance, but specifically for the gaming industry. I mentioned earlier that when you've got to the problem where you've got servers that are actually playing, you don't want to saturate your bandwidth to your local machines. So you need to bear that into mind when you're actually transferring the updated builds to them. And that system takes care of all of that. As you can see here, we actually do a transfer from dev instance. So the main build will be grabbed from the image source, of which we've got a number of several built-in ingesters. The first off is Steam, and the other one is S3 Bucket. So make it really easy to be able to just grab your build onto your dev instance, make sure it runs so you can do a quick Q&A pass, make sure everything's in place and somebody's not forgotten to put a key DLL in there so the server crashes on start instantly. And then once that's done, we actually take a difference analysis. And so we only transfer the changes, which makes it much more efficient in terms of your bandwidth. On the BDP issue that I mentioned earlier, the solution that we've got to that is we actually use parallel data stream transmission across the entire network. So we never open a single connection between either the dev instances and the mirror or the mirrors and the instances themselves. They're all done in a parallel transfer. But on top of that, it's a streamed compression transfer. So one of the problems that we see quite often in the industry is whereby people will transfer the new build, and they transfer the new build, they download it to the disk, they uncompress it from disk and write it back down to exactly the same disk. That means you're touching the disk at least 3 times to make sure that you've actually got the build on the box. And all of those are going to be increasing the possibility that you're going to be impacting your game servers, which are running on your hardware already. So we use an in-flight stream compression system, which downloads, uncompresses in memory, and then only writes to disk a single time. So what is the process that we've got? We've got a fairly simple 3-stage process. First of all, we do an update. In this case, we're just doing a Steam update. So if you've got an existing set of infrastructure that already creates your build and deploys them to Steam, we can pull it directly from that. There's no changes needed. And then, as I mentioned, we create this difference. The difference is there to save bandwidth and improve the performance when deploying new builds. If you've got a little hotfix build that you're doing out to fix a server bug or a client exploit, you want to be able to deploy that really, really quickly. So you don't want to transfer what could be a 5-10 gigabyte full image build update to all of the boxes. And that's where the difference analysis comes into play here. And finally, once we've got that difference analysis, you can confirm it, and we create a separate game image version that gets uploaded to each of the boxes. So you can see in terms of what we actually store on the machines, we store many different game images, and each one of them can be used at any one point in time. So if you did have a problem with new build X and you were in the situation that you had to roll back, you can do so instantly without any problems. So I mentioned zero downtime patches. The way that we do this, we've got multiple production images. In this example, we've got all of the production images running on version 1 for PC, PS4, and Xbox One. And you'll notice another feature on here that I think is fairly unique in terms of our offering, is that we actually run all of the different game builds on the same instances. So if you've got a spike in player demand for your PS4 build, you've just done a promotion, maybe a free weekend on PlayStation Store or something like that, and you get an influx in capacity requests for PS4, that doesn't make any difference. We can still allocate the capacity from what is there, and you'll just see an increase in density on the PlayStation 4 side and a decrease on the other sides. And how we do that is at each time an allocation comes in, the system knows exactly what build any specific server is actually running, and it can switch it on the fly with zero downtime. We also have the concept of retired images. If you've got a new build that you've just pushed out and everybody's got it, you don't want to be shipping out the old builds onto new capacity as you're spinning them up. So we enable you to retire the old builds and only spin out the new ones. And as you can see, I've already mentioned there, the platform capacity sharing. So one of the issues that is quite common is the fragmentation problem. And if you're running all of your platforms across homogeneously on the same architecture and on all the same hardware, you don't have any fragmentation problem there because it's all sharing the same capacity. And as I mentioned earlier, it's you get the optimized for deployment of hotfixes, whereby if you've got a small build that you want to push out, that's not a problem. And that's what you'll see as active allocations are coming in. You'll be getting the new builds flicking through, and you can see that we've just deployed build 2 of all the Xbox One, and you've got a number of servers that are on there. But it doesn't mean that everybody's on it. If you deploy your client fix, not everybody actually downloads the client at the same time. So you still might have some old people playing on your Xbox One build, on build 1, which is still available. You don't have to have that hard cutoff that you might have otherwise. So this is it in action. Titanfall 2, a couple of weeks back, I think it was, John. Patched the PC version and the Xbox version, and this is the PC version rolling out. You'll see that there's actually a downtrend in terms of players, but this is not a downtrend in terms of server capacity. The server capacity is all instantly available, but clients do have to spend some time to patch, right? So that's the player drop-off as they come out of the game to patch their clients and then come back up with a new capacity there. So in terms of auto-scaling, how do we handle the auto-scaling? First, I'm going to cover off a little bit of terminology, just so you're aware of what I'm speaking about when I'm going through the various things. A fleet in our system is used to create separate environments. Separate environments are actually specified really around similar resource requirements. So if you did actually have 2 games which are running very similar resources, there's nothing to stop you putting them actually into the same fleet and getting even better server usage density across the farm. Each fleet has 1 or more regions. So when you're allocating into the fleet, if you want obviously for low latency games to make sure that you've got players in the specific region that they want to play in. So a region is just a set of location providers, and that location provider is actually including DC availability zones when you're moving into the cloud. So we take into account the fact that you've got 4 or 5 availability zones maybe in a specific region, and that gives us just increased redundancy along the lines of when you've got the multiple actual clouds playing in there as well. So a bit of the basics on how we scale. Fleet regions are scaled independently. So if you've got capacity in Russia scaling up, it's totally independent from the capacity in the US. And we know at any point in time what servers and machines are actually in use. And that allows us to scale very, very accurately to what capacity you actually need. The relative cost of each of the machines is also taken into account. So when we've got a hybrid model where we're using the cloud and bare metal, we're obviously going to take into account of that, and we're going to allocate to the least cost machine first. And one of the key things that we do slightly differently from others is that everything is event triggered. So allocations and deallocations that come in from the tech from Strider's side in terms of Titanfall 2, at every one of those that comes in is a scale point question mark within the system. So we're not ticking over and we're not saying, oh, we're going to see whether we need to scale every 30 seconds or every 40 seconds. At every single allocation, deallocation request, we're making another decision point on whether we're going to scale up or scale down. So if you've got a big spike in demand, you're never going to get caught short in terms of that. And also we've got manual scheduled events. So if you've got a big DLC release that you're expecting a lot of new players in there, you can take that into account and force the system to scale up ahead of time and make sure you do have capacity to be able to keep that in play. And descales and allocations, one of the problems that you'll see is when you're trying to make a decision on whether to get rid of a specific piece of hardware or whether it's actually in use. If you make the decision that it's actually not in use and then you go to descale it, and an allocation has been made, you're going to get an upset player because they've just gone to play on that server and the server's actually gone. So within the system, again, we love Redis too. And everything is made atomic by making decisions within Redis on whether to scale or create allocations into the system. So we actually have two different methodologies in terms of how we enable you to scale up and scale down. There's some commonalities between the two. The key ones are the fact that requests and processing are 100% async. We made that decision to ensure that we could deal with a very high volume of requests coming in. We didn't want large, long-running requests sitting around in the system. And I'll come on to some of the benchmarks a little bit later, which I think proves that that was a correct decision to make. And all requests are idempotent. Everybody in the room know what idempotent means? No? Okay, so if you replay a request coming into the system more than once, you're still going to get the same answer. Now, one of the key reasons for doing this is if you're allocating and creating capacity based on demand, and if there was a network glitch in the middle, you don't want to have to make that request twice and end up with twice as much capacity that you requested. You always want to get back the original capacity that was actually allocated when the system actually got the first request, but you never actually got the response. So that's why we make that idempotent. So the two different methodologies that we use are allocations and reservations. Allocations requires the control of players joining. So it requires a solution similar to Strider for Titanfall 2, whereby Strider is actually requesting capacity on each match to be able to allocate it to. That gives us a very good view of the system and allows us to defragment very, very quickly, as Jon's mentioned. Reservations is something that we added to make it simpler to integrate for games that actually are already in production and couldn't actually make the changes required into their matchmaking system, for example. So it's still just a couple of calls. So essentially all you have to do is say, I'm in use or I'm not in use, and that still gives you the ability to scale up and scale down. It does have a couple of downsides. You do get increased fragmentation because the system can't actually choose where to place the capacity. It's just taking information from the servers themselves, and that obviously has a cost implementation as well. And it does make scaling slightly racy, where I explained before, if you come to descale a piece of capacity, and we make the decision to a player joining it, you've got that small time period of which the player could go to join, and that capacity is just being descaled. So that is that. So when we first started looking at the various cloud scaling technologies, we wanted to prove to ourselves what were the pitfalls and what were the benefits of each of the scaling platforms that were out there. So we started doing some benchmarking. That benchmarking led us to some interesting results, as you can see on the screen there. Creative an entire Windows 2012 VM on Google takes just 3 minutes. In comparison, exactly the same creation on AWS on a good day takes 9.5 minutes. They're both very similar in terms of boot. So we actually have the concept of scaled down standby capacity within the system. So we can actually create capacity ahead of time and then shut it down. And then as the demand increases, all we have to do is spend the 1.5 minutes booting it back up again in both cases. Shutdown times are a bit variant as well, but once the shutdown call has been done, then you're not paying for it, so that's all good. But one of the key kickers here is billing. Billing for Google Cloud Platform, you've got that 10-minute plus the 1-minute increment. So if you decide that you need to scale up your capacity and that capacity is only in use for, say, 45 minutes, on Google Cloud, you're actually going to be only paying for 45 minutes, whereas on Amazon, you've still got that minimum hour, and that gets even worse as you scale up. So in addition to the timings, we also wanted to make sure that the system was capable of scaling up well ahead of time. And one of the problems with scaling ahead of time is you're making assumptions on how quickly you're going to get the capacity. So in the examples before, those were all the best case scenarios of how long it takes to get the capacity. But we did some research whereby we actually did scaling up and down in every single location that each of the providers support. And we found that there was a very high difference between the two platforms that are available. The time variance on Google Cloud Platform for scaling up new instances was actually a very low. We were looking at about 20% variance when we're hitting it with the same amount of requests. Whereas on AWS, the variance was very, very high. And in terms of very high, I'm looking double or triple the time to spin up. And that was actually not only location dependent, it was actually time dependent. So if you requested a VM at AWS's peak times, you're actually going to get a much slower response. And if you're trying to predict and stay ahead of the curve and make sure you've got capacity for your gamers, you need to know about this. And the last point on our slide here is about IOPS latency. When you spin up a brand new VM, you want to make sure that it's performing well. We were really quite surprised at the difference between a cold VM and a warm VM. And we used them for our mirrors as well. And one of the things that we saw, we were seeing latencies in the hundreds of milliseconds for every single IOP that we were making on a cold image. And this actually totally destroyed the performance of all of our mirrors at one point when we initially started testing with AWS. So we have to take quite some extreme measures to work around that problem. And what we do is we warm up the mirrors when they come online by actually literally reading every single file off disk. If you look at the technical architecture behind it, what you'll actually find is when you spin up a new copy of an image, it actually is copying off an S3 backing store into a local SAN before it then gets used. It's all transparent to you, unless you look at the latency figures, and then you can see some quite stark pictures about that actually happening in real time. So what is our decision-making process? As John said, Redis, it's awesome. Use it if you haven't. We use extensive use of both Redis sets and Lua to make atomic decisions. In terms of how we order our allocations, we obviously choose the lowest first, which is always going to be the metal capacity, and then cloud. And we also actually choose the most active servers. So if we've got a VM with 7 servers in use on it versus a machine that has only got 3 servers in use on it, we're actually going to prefer the one with 7. So we build up the capacity to its absolute peak. And the reason for doing that is effectively being able to downscale. It's not an upscaling problem, it's a downscaling problem. So you want to be able to make sure that you can get rid of capacity as quickly as possible. So that's why we do that. And in terms of descaling, obviously most expensive goes first and then longest idle, again, for the same reasons. So capacity scaling up is easy, right? Just spend lots of money. The prediction is a really hard thing to get right. There's lots of variables to take into account, and it's not as simple as you might think when you first look at the problem, predominantly around variance on getting VMs up and running. So having standby capacity really helped our solution in that respect. And then if you've got sudden demands of player spikes, you can mitigate it to a certain extent by making sure that your provider is aware that you're doing a free DLC. Be surprised at how many times we have a free DLC and the provider forgets to mention it. So that's a good one. And then we've got the fact that all of our capacity is monitored in real time, as I've already mentioned. In terms of what we do to trigger up, so when we're scaling up, we're always monitoring the available capacity. So we've got a figure that you can alter on the fleet level or on a specific region, which enables you to tune how far ahead and how much capacity you want in advance to make sure that your players have always got capacity available. But we do a lot of automatic processing in the background to make sure that when we see that you've inputted that figure, we're taking into account the fact that the VM times, not only the VM times, actually copying the images across as well. So if you've got a very large game server, we'll actually be scaling up more in advance than if you've got a very small game server. And some safety limits. Max servers, you don't want to have a bit of a mishap on the allocation side and request 200,000 servers and spin up lots of, yes, John's nodding. Yes, we did have an incident in dev where that did happen. Yes. So, and scaling down, that's all about cost control. You've got the two levels of scale down. I said we've got shutdown and delete. Shutdown's a really good way of actually getting rid of capacity, but having it available at a very short period of time, that 1.5 minutes to bring that VM back up again and actually get it running and all of the capacity that it has available. And we do it really simply. We just base it on a TTL. So if an instance hasn't been used for a certain amount of time, we shut it down. If it hasn't been used for an even longer amount of time, we get rid of it. So it enables the system to very quickly and simply reduce capacity to make sure that the costs are kept to a minimum. And those safety limits are basically the inverse of what we did on scale up. So how did we test this system? When we wanted to launch Titanfall 2, the guys were wanted to make sure that our bold claims about what our system could do was actually what it could do. So we took advantage of GCP. We got some really high cap limits on our account, and we scaled up 1 million players worth of capacity in just 12 minutes. And all of those VMs were provided by GCP in a single region in just 8 minutes. So some really good performance there. And this was all achieved with a then unoptimized Python celery stack, which is in the midst of being replaced with some more Go. And to give you an idea of how quickly and how well Go does with processing systems like this, now microservices, our fleet manager instance, which is the front door to all of allocations and deallocations, a single instance of those, which is running on a single 8-core box, can handle 4,000 allocation requests a second, 3,000 deallocations, and 4,000 checks per second as well. So each one of those is going to give you an estimated player capacity of between 30 and 40 million. So the system really does scale. So what are the success stories? Obviously Titanfall 2, which John's here talking to you about, which used the full allocation system. But we also, a week later after launching Titanfall 2, we also launched Tripwire's Killing Floor 2 on the reservation system. So both are proven, battle-tested solutions. But how do we monitor all this stuff? We basically measure everything. like everybody should do. But we also don't reinvent the wheel. So we use the right tool for the right job. For any of you DevOps that might be out there, if you use New Relic for monitoring your app servers and you want extra visibility of what your database servers are doing, have a look at Vivid Cortex. That's an awesome application to be able to monitor every single thing that's going through your database, not just the ones that New Relic will allow you to monitor. And it gives you much more insight into exactly what it's doing. And then we've got alerting into Slack, the usual things. And in our internal API uses visualization from Influx and Grafana. So why is it so important to measure everything? Well, when you don't measure everything, you don't see everything, right? So we had 2 different game types running, and you can see here that the capacity is pretty similar, but the player density figure, which is one of the metrics we base on how efficient the system is providing, is wildly different. In this particular case, the efficient game mode there is up in the 80s in terms of how dense the player population on the instances themselves are, whereas the one below, we're down at 50%. So there's a significant cost saving to be had if we fix that problem, of which the Respawn guys did. And you can see on the orange line there, the player density going straight up after the fix was deployed to Strider, and that improved the player density from 40% all the way up to 90%, and resulted in a 20% required capacity drop. So there's significant savings to be had there. But why do we do the hybrid model? John's touched on the cost element, but there's also a lot of other elements to it. We want to make sure that we're in a strong commercial position to be able to get the best deal for all of our customers, but we also want to adapt the innovative new products. So when Google do the per second billing, I'm sure we'll be using that. But it also gives us that massively wider geographical coverage. If we've got the capacity to use all of the different clouds and all of the different bare metal hosting providers that we work with, we've got a very good coverage of the globe. So if your game is really latency sensitive, that's one of the key reasons why we chose to do the hybrid model. And obviously it increases capacity. As John has again already mentioned, the fact that we did run out of capacity in a well-known cloud, not Google. We want to make sure that, even in that worst case scenario, we want to be able to allocate across to something that's not quite so close, but it gives us options. And the redundancy is there. Provider outages happened. Yes. 2 days ago. No, yesterday. S3, whoopsie. And we did have during tech trial quite an interesting one. We had a location exchange problem. So it was Time Warner Cable was actually one of our biggest player bases where they were coming from for Titanfall 2 within the tech test. And we started seeing really increased latencies. And that latency increase actually turned out to be the fact that Time Warner Cable's connectivity to Google was running extremely hot, and they were just dropping packets left, right, and center. If we'd have been on a single provider at that point, we'd have been stuffed. We wouldn't have been able to do anything to help the players of the game. But as it was, we didn't want to because it was a lower latency normally. But in this scenario, we actually disabled Google Cloud, switched across into Amazon, spun up some instances there, and the capacity just moved across seamlessly. So it's not the ones that you always think about, but there's some uncommon ones as well. And that, I think, is an example of Johnny being really happy about this happening. You can see the players spiking up and down there while we were investigating what the actual cause of this unexpected issue was. And then when we identified what it was, we checked the paths through to the different data centers and switched over capacity between the two. And you can see it scaling up and scaling down from one to the other. And it was all transparent to the players. So that's me done. Does anybody have any questions? You got the mic.
Here we go.
So when you're optimizing, do you optimize, like for example, with Google Cloud versus AWS in terms of the pricing? Do you optimize for like post-peak behavior? So if you have to spin something up, presumably at post-peak, it'll be more likely to have to come down more quickly. So do you say, okay, we'll use Google in this case because we suspect it'll have to get shut down quickly, and so we can use the 10-minute pricing?
One of the reasons that we really do at the moment prefer Google's model over AWS's, for example, and that's across the board, is because of that smaller increment that they allocate on in terms of a pricing. So it's always more efficient to be able to spin it up into Google. So if we do have that choice, that's where we do. If that decision point changed, then that's totally flexible and the system will compensate for that.
But it's not an optimization across time, it's an optimization a priori. So say we always prefer Google?
No, it's a dynamic thing that can be adjusted on the fly. So if the pricing model changes or your decision point changes, say you got a really good discount on AWS, then you could adjust that on the fly and the capacity would just move within your game period.
Okay, so are you analyzing that all the time, or is that something the studio Respawn tells you, okay, now in light of this, we want to change?
You can do either. We do monitor it internally, but if you want to override the decision and switch it, then you can do that too.
With the recent explosion of sort of tier 2 hosting providers, things like Vultr, things like DigitalOcean, et cetera, like Amazon Lightsail, et cetera, are you finding that the cost models that Jon showed us previously are no longer valid, where those services are offering something like $5 per terabyte of monthly transfer, that at that point that becomes cost competitive with bare metal?
That is a very good point. And the way that we design the system is to be able to integrate into new clouds as and when they become available. So, you know, if the pricing model does get turned on its head by a new provider and that provider does give us the service that we want, you know, service is also a paramount of importance to any game host, that we don't want to put the capacity into a host where the service is going to be terrible. They may claim that they've got huge amounts of bandwidth, but do they? And that's some of the things that our tech team always test before we take on a new provider. So yes, if it does vary wildly and change itself, we're going to be able to take advantage of that. That's going to be a great opportunity for everybody to make some good savings.
Have you guys noticed a difference in hardware reliability between the platforms? And do you take that account when load balancing?
We don't take that into account in terms of load balancing, but yes, we have noticed a difference. We have had one single allocation failure from GCP. We've had quite a few from AWS.
Any pain points for GCP that you'd like to bring up or point out, things that they can improve?
No, we did have the incident when we were doing tech trial and the capacity that we were looking to put into tech trial, and there was, I think the US didn't actually have enough capacity that we were expecting, so we had to balance the load between GCP and AWS, but that was something that's already been addressed quite quickly from the Google side, which is great to see. Well, if that's all the questions, I will hand over to Miles, who's going to give you the last bit.
Awesome. Thank you very much, everybody, for taking the time. I will be shorter and hopefully less of a pain in the ass. So Google Cloud Platform is one of the ingredients that made this system work. We're proud to do our little part of it. And I want to explain some of the places where what we're offering is a little different than our competitors. I was pretty fascinated. I hope all of you are tracking all of this at the degree to which the conversation that we've had today about the way that this is all implemented is entirely bounded by the use of virtual machines, right? Like what the building block we're going to use here, ladies and gentlemen, is a virtual machine, and that's how it's going to work. That's a little unusual. And Google's done a lot of work to make it so that our virtual machine environment behaves very differently than other public clouds. So I like that we get grouped into the sort of cloud subsection, but they're built really weird here. So how many folks have heard of containers? Yes, containers are pretty groovy. How many folks expect that we know a thing or two about those? Yeah, we invented the Linux C group, which is what powers all containers, and open sourced that 10 years ago. So all of our virtual machines are running in a container. There are no actual software applications at Google that don't run in a container. We run about 8 billion of those now every month that get booted. So the VMs that get consumed for this project are running inside a container. What does that allow them to do? First, what you're talking about, there was a discussion earlier about what's the availability or how frequently do the VMs fail or what's the uptime associated with that. We've built a function called live migration that allows us to take running virtual machines and move them from host to host. We do that while they're under load. We do that while they're writing at 400,000 IOPS to 1.5 TB of local solid state disk. We do that while they're interacting with their variable attached to GPU and SSD devices. We know that that works for every VM because we've migrated every VM every week since we launched the product. Because that's the way we update the server hosts for new kernel patches. It's a security thing. We're trying to make sure that all the VM host infrastructure is secure, and so we have to patch it very frequently. If your VM provider is not rebooting the machines or has some technology like this to move them around, they haven't patched them in a while, and that's a problem. So the other thing that it allows you to do if they're containerized is I don't actually have to bin pack the physical host in power of 2 subdivisions. So we have a thing called custom virtual machines where you can tell me I want 18 core VMs with 26.75 gigs of RAM, and I'll charge you exactly for what you've used, and that'll be what you pay. So in this environment, if they are able to find even that the game server needs 0.5 GB less RAM across all the machines that are running, they can reduce that from their fleet and they stop paying for it. Other providers, because they're not built on container tech, don't have the ability to do that. We're also enabling a thing called sustained usage billing. So any machine that does run 24/7, we automatically chop 30% off of the cost. So all of that adds up to a VM environment that's cost effective, that's very efficient. Now, you are totally right. If you go buy a computer today and you can load it 100% for more than 5 days out of a month, it will cost less than my virtual machines. Ouch. Wow. So if you have a good, clear ability to predict, and you have the ability to contract with folks that can get to bare metal infrastructure and can deploy that reliably and accurately, you can save money over public cloud, assuming you estimate correctly. So the most recent game that I worked on, their estimate to us was they thought very aggressive. We actually tripled it. They said that they were going to consume 50,000 queries per second against our data storage infrastructure as a measure of the overall growth of this that's far enough from their user count to be safe for them to share. Their actual load 2 days in was 52 times that. So not 200%, 5,200%. So it's really critical as you're building games. The other direction can happen too. You can say, we're going to need a bajillion machines. And in reality, you need 6. So anytime you make those predictions, you have to anticipate that it's, how many folks are currently working on a sequel? Or a 3rd or a 4th or a 15th or a FIFA 9722. Those games have better predictability, have a clearer idea of what game traffic will look like. And I think that you can move to more and more conservative consumption. If you're doing something brand new and you have no idea, I would certainly recommend including cloud as a component because we're a hell of a shock absorber. So we do have our own separated and custom built virtualization and hypervisor layer. All of that stuff's built at Google. Allows us to do some things to boot much more quickly. You guys are seeing about 1.5 minutes. We have some changes that are coming that are even reducing that time frame. So important for folks to check that. And I agree with the warm startup pattern as there is a whole bunch more procurement that's happening on our side of resources at first instance creation as compared to just being able to turn virtualization on. it is super important to track shutdown times. You saw in the last presentation the difference. Ours take longer to shut down in course. We don't actually charge you during that shutdown period, so it's not something that you end up paying for. But a lot of people's automation can struggle with keeping track of all the rest of the machines as they move downwind. But again, this is all the building blocks oriented around the virtual machines for the actual game servers. I'm super interested in what we're observing, not just with Multiplay and with Respawn, but with lots of game developers, where the core allocation and application management, the databases and storage infrastructure that's being used to power allocation to games becomes a very big differentiator in being able to capture this kind of efficiency. So there's a lot of new tools. Folks like Redis, I heard that we have coming out next week, very important news on the subject. We have this event you may have heard of called GCP Next. Most cloud providers do things like announce new products at those sorts of things. So that might be one to pay attention to in next week's Hacker News thread or whatever you're watching. We also have recently released a very powerful database, a thing called Spanner. How many folks have heard of Spanner? So Spanner is the monster. One of the kinds of things that you can't build in your own data centers. Right? I say that sort of bluntly and directly, but it's true. Spanner depends on having a cesium clock in every one of multiple buildings, GPS units on all of the racks, so you know exactly where they are physically, military grade GPS, so you have millimeter range accuracy, and you have to have distributed software. What that allows us to do is have a totally relational, normal SQL syntax, square, tidy database that'll do millions of transactions a second, globally transactionally consistent. So I can add users in Tokyo to my database and check to see if that user exists in Europe, and the answer comes back consistent every time. Doesn't matter where it is on the planet. If you squint really hard at it, you might say that it violates the CAP theorem, which is this thing that bounds the behavior of databases. But the guy who invented the CAP theorem, his name's Eric Brewer. He's on the Ing team, and he says it's okay. So yeah, so we're cool. So those kinds of building blocks are also something that can help as you build application layers to orchestrate these kinds of raw materials. We're seeing that pattern quite a lot, where platform as a service or database as a service components get used to reduce the overhead of implementing all of the stuff other than the core of your game. So I was super happy when I played. I won. I did, in fact, get punched in the face by the guy, and then I got thrown by the robot, which is really super fun. And I made a super serious point of only playing on the GCE servers, because that's just sort of how I go. GCE does not stand for, like, you know, general computing energy layer. No, that's actual, when you were on those machines, you're on the ones that were us. And this network of infrastructure that is lent out, that's all totally private, Google-owned fiber. So every one of the packets that move around the web on this network, Google controls, gets done by us. That's 4 times the throughput of the public internet today. So we have a little extra capacity here. We're looking forward to running your games on it. We think that generally you'll find that this is something that will just work. We're hoping that all of the materials, not really, frankly, just from our public cloud, but all the public clouds, these kinds of raw building blocks are rapidly becoming commodity, are becoming a thing that should just be easy to consume and reliable. And we're getting to a place where you should be able to choose based on the price performance measures and the reliability that you're measuring from your actual consumption of the service above any other issue. The other stuff that I talked about, Spanner and the other kinds of cool tools, I think there's still a lot of room for differentiation up top. But down in the pavement, we're getting to the place we all wanted to be, where you can just sort of chew computers as you need them. And we're excited about that. Thanks. Super stoked. Any questions? Open season. Google has all sorts of weird stories. Good.
Can you talk a little bit about the secret you're talking about, like noisy neighbor problems? So we suffer from that at all?
Sure. So I worked at AWS for 4.5 years, so I have just a little bit of insight here. When you run Zen-based hypervisor virtualization, even the most modern version of Zen, you have control over RAM and RAM throughput, the bandwidth from process. You have NUMA control, which side of the core you're on, and CPU level. Our virtualization has those two controls, as well as network throughput control, PCI bus lane control, access to the SATA drives, if there are such a thing. There aren't very many of those left anymore, and other components of the internal system that we use, access to the security hardware, things like that. So by having higher granularity of control, it allows us to reduce noisy neighbor, particularly on network. Now we're also 60% denser on network. You can get 16 gig on VMs instead of 10 gig, and that's not the whole pipe, right? Anybody found a place where you can buy a 16 gig network card? I didn't think so. So you're buying a chunk of what we actually have, and we reserve a bunch of that to reduce noisy neighbor. The container-based system allows us to just like we can move because the hardware is breaking, or we can move because we're patching the instance, we can also move if there's somebody that's doing something particularly unusual on a machine. And we've done that not only for CPU level overload, but network overload and SSD overload as well. So there's a lot of controls against that. Yeah. Open season. Go ahead.
So you say you've got all this bandwidth.
Bandwidth.
Where's the cost coming?
We're never lowering the cost. It's so awesome taking all of the monies. So today, what you pay for is 77 points of presence pre-deployed around the planet with terabits and terabits and terabits of egress capacity that you don't pay for up front. Right? In the same way as the computers are sitting around available, the bandwidth is sitting around available. We are working with lots of customers that will build what's called a GCI, a private interconnect to us, where instead of paying 12.5 cents per gigabyte, you pay us 2 cents per gigabyte, just the egress cost, and then you go negotiate your internet rates. Now, the problem is that means it's your problem to figure out. Some businesses are very good at that, have a bunch of relationships already built in place. I suspect Multiplay could do a good job of that. Most companies cannot wire that out and figure out how that works. Now we are having an event next week where cloud providers like ours make announcements about all sorts of things, just sort of throwing it out there. Nudge is as good as a wink to a blind bat. That's right. Anything else? Let's go make some games. Thanks.
Brilliant. That's it from a multiplayer perspective. Thank you very, very much for coming out. Thank you very, very much for Google. We've been an amazing partner through this whole journey and for hosting us today. And I think just one final round of applause for the three speakers, Jon from Respawn, Steve from Multiplay, and Miles from Google.